Section 6.1, estimating with finite sums. We are looking now at area under curves, so we're stepping away from derivatives for a little bit. And before we dive into how to approximate the area under a curve, we want to look at some different curves and think about what the meaning is of the area under the curve. And to figure that out, the best thing you can do is to think about putting one rectangle under the curve, and how would we find the area of that rectangle? What would the units be? So we have time in hours on the x-axis and miles per hour on the y. So if I wanted to find the area of that rectangle, I would do base times height, and the base would be in hours, and the height would be in miles per hour. And when we multiply those two together, the hours will cancel, and our unit ends up being miles. So the area under the curve of velocity versus time is measured in miles, and miles measures distance. So the meaning of the area under that curve would be, and this is where I need you to be very careful, it would be the change in distance from time 1 to time 2. Not just the total distance, but the change in distance. Okay, so if we look at our second graph, we have force on the y in pounds and distance on the x in feet. So again, if we think about one rectangle underneath there, if we use one rectangle and found the area of that rectangle, we would be having feet times pounds. And force times distance is, in this case, in foot-pounds. This is the rectangle that we're finding the area of. And foot-pounds is a measure of work. Now, so we have shown two examples where we put one little rectangle under the curve and find the area of that. And our first method of estimating areas under curves is called a Riemann sum, and that is when you use rectangles and fit as many rectangles as you can under the curve, and then add up the area of those rectangles, and we have the area under the curve. And if we could go to an infinite number of rectangles under the curve and sum that up, that would be the exact area under the curve. Now let's look at our first example. We have a velocity curve, v equals t squared. A particle starts at x equals 0, so its initial position is at 0, and moves along the x-axis with a velocity v of t equals t squared for t greater than or equal to 0. Where is the particle at t equals 3? Well, when we find the area under that curve of velocity, the shaded area represents, again, very important, the change in the distance. So we'll underline change in distance. That is what is represented by the area under that curve. Since we started out at x equals 0, our distance, or to find out where the particle is after 3 seconds, we would add the area under the curve to our initial position, which is 0. If our initial position were 10, we would do 10 plus whatever this value comes out to be for the area under the curve. Okay, the next thing we want to look at is the different ways that we can approximate the area under the curve. I'm sorry this came out a little blurry. It says using rectangles to approximate area under the curve. And the first method for a Riemann sum that we'll use is a left rectangle approximation. Your book calls it LRAM. So we have, again, our function v of t equals t squared on the interval from 0 to 3. And we want to break it up into 9 subintervals. You'll always be told how many subintervals, and in this case we have 9. So you always want to draw in the subintervals first and then draw in your rectangles. So a lot of students think when I do a left rectangular approximation, I draw to the right. So I've started putting in the left rectangles, and now I want to continue putting those in. So we start on the furthest left of the first partition, which is actually at 0, and we draw in our height. Then we go to the left side of the next partition, which is over here, We go up to where it hits the function, and we draw to the right. So let me get a line tool so it comes out a little cleaner. We draw to the right. Then we go to the left side of our third partition, go up to where it hits the function, draw right. Fourth partition, this is the right side, this is the left side. Take the left side, go up to the function, draw right. So we'll draw the rest of these in. And then what we would do is we would sum up the areas of these 9 rectangles. Notice when you do a left rectangular approximation, you start at the left side of your overall interval. We started at 0. And our last partition that we use is actually the one before our right end of our interval, because we're using the left sides of each of these intervals. Down here we have a right rectangular approximation. So again, you would be told how many subintervals, and you would be told what kind of approximation to use. So in this case, in each subinterval, we go to the right side of the interval and draw to the left. In this case, we'll have to go left and down. And so for our first subinterval, we go to the right side, which is just a little above 0, and then we draw down. Mine are going to be a little crooked, but I think you can see them. Right side of each partition determines the height of the rectangle. And so what we need to remember is the height of these rectangles is being determined by the function. So our function here is t squared. So we would take the x value of the right side of the partition, like right here we would take 2, and we would plug it into t squared to get the height of that one rectangle. Let's see. So there we have all of our right rectangles, and we would sum up the areas of all of those to get the right rectangular sum. We can also do a midpoint sum. And the midpoint sum, we will need to find the middle of each subinterval, go up to the function, and draw left and right. So I've drawn in the first 1, 2, 3, 4, 5 of them. Let me show you how we get the 6th. So I find the middle of this subinterval. I go up to where it hits the function. I'll put a point there. Hits the function right about here. And then from there, you draw left and right. And then we'll draw down. So again, we find the middle of each subinterval, go up to where it hits the function, and then draw left and right. Just another way to approximate that area. So I'll finish those up. Okay, let's look at the calculation I have down at the bottom. I've shown the calculation for a left rectangular approximation, the one that we saw above. 1/3 is the width of our subinterval. So we had 0 to 3, it broken into 9 subintervals, so each subinterval is 1/3 in width. And then I start at 0, and I plug in the x values on the left side of each subinterval into our function. So 0 squared I don't show here, but 0 squared is 0. Then the left side of the first subinterval was 1/3. Plug that into the function, which was t squared, so that's 1/3 squared. And then we continue, 2/3 squared, 3/3 or 1 squared, 4/3 squared, 5/3 squared, 6/3 squared, 7/3 squared, 8/3 squared. And notice we do not do 9/3 squared because we're using the left side of that last subinterval. So we work from 0 over to 8/3. When we do a right rectangular sum, we would start at 1/3 and go all the way to 9/3, using the right sides of each of them. Okay, the next thing I wanted to show you is a way to set this up in your calculator to make the work a little easier if there are a lot of subintervals. So I have my left rectangular approximation, and I go to Stat Edit to get to my lists. So Stat Edit brings up your list. You want to make sure your lists are cleared out, And when you clear out a list, you need to put your cursor right in the header, right in L1, and then press clear, enter. All right, so we want to put in all the left sides of our subintervals, so 0, 1/3, all the way up to 8/3. And then in L2, you're going to plug these x values into our function. Well, our function was v of t equals t squared. So in our L2, we're going to go up to the header. Again, you need to be right on the header. And when you're on the header that says L2, type in L1 squared, or second 1 to get L1 and then squared. Then in L3, what we want to do is we want to take L1, oh, sorry, we have an error in our notes. Let me fix that. Okay, so L3, we should take, again, put your cursor right up in the header of L3, and type in L2 times 1/3. And what we're doing here is we're taking the height that we put in L2 of each rectangle and multiplying by the interval width. Again, this will change for each problem. Our interval width came from 3 minus 0 over 9, because we are going from 0 to 3 and we have 9 subintervals, so each one is 1/3 of a unit wide. So we have, that is how we can get our interval width. And if we're on an interval from A to B, it would be B minus A divided by the number of subintervals. All right, so when you do L2 times 1/3, you'll get a list of values there for L3. Then you go back to your home screen with second quit, and we want to sum up the values in L3. To get to sum, it's second stat math 5, and L3 is second 3. And when you sum that up, I believe we get 7.55. Let me double check. Yes, so we get 7.55 for our left sum. All right, and then further down, I had set up our right rectangular approximation. We need to make the same correction on our notes here. I will take care of that. Okay, we're good to go here. Now, we would be using a right rectangular sum. So this time, the main difference is in L1, we don't start at 0 like we did on the left rectangular sum. We start at 1/3, and we would go all the way to 9/3. Everything else is done exactly the same. And if you practice this right rectangular sum on your own calculator, you should come out with 10.555. All right. Finally, we had the last page of our note packet was an exploration. And I assigned this as a lab due Monday. And the exploration is 6 rectangular approximations. This time, we only have 3 subintervals, so, oops, sorry. When you do this, your subintervals will be here. Oops. Here. And here. And the first one we're doing is a left rectangular approximation. So in the first subinterval, the left side is at 0. We go up to where 0 hits the function, and we draw right. And in this case, it leaves right and down. Use the left side of the second subinterval and draw right and down. And the third one, right and down. So there are your 3 subintervals. And I want you to find the left rectangular approximation for that. Then on these 2, you would do the right and then the midpoint. And please note your function this time is y equals 5 minus 4 sine x over 2. So this is what would go into that L2. You have another option where you could put this equation in y1, and then in L2, you could just say let L2 equal y1. So you don't have to keep retyping that whole equation. So that's something you might want to consider to make it a little bit easier to get through these. All right, then after you do these three with this function, 5 minus 4 sine x over 2, the other thing you have to do is if f of x is a positive decreasing function like the one we have here, then LRAM, I want to know if it is an overestimate or an underestimate. And I want to know if RRAM, the right side approximation, is an overestimate or an underestimate. One other thing to clarify, when you put this equation in y1, you will not be typing x here, you will be typing L1. And then let L2 equal y1. Okay, so if you were absent in class, you're going to want to pause this and get a printout of the lab. And let me get a clean screen for you to do that. Okay, so here is the first function, y equals 5 minus 4 sine x over 2, and 3 subintervals, and I want a left rectangular approximation, a right rectangular approximation, and a midpoint rectangular approximation. And then you will tell me if f of x is a positive decreasing function, then LRAM will be which, an overestimate or an underestimate. And now let's get down to the bottom 3 problems. So our next function is y equals 2 sine x over 2 plus 3. And you'll do a left rectangular, a right rectangular, and a midpoint. And given a function that is positive, a positive increasing function, then LRAM, will that one be an overestimate or an underestimate? And will RRAM be an overestimate or an underestimate? All right, hopefully this helps, and I'll see you on Monday. Homework, by the way, is, let me find it for you. The homework assignment is page 274, 1 through 3, 19, 28, and 30.